So let's do the first one. It's the sum as I goes from 1 to 6 of I. So the first one is 1. And then we substitute the next value up, and notice it's plus because that's what sigma mandates. 2 plus 3 plus 4 plus 5 plus 6. And I suppose you can add those up. That's 6, 10, 15, 20. Okay. This next one is starting at 0 instead of starting at 1. Pretty typically they're going to start at 1, but I just wanted to expose you to different start and stop points. So if it goes from 0 to 5, we're going to plug 0 in first. 0 plus 1 is 1. Then 1 plus 1 is 2. Then 2 plus 1 is 3. Then 3 plus 1 is 4. 4 plus 1 is 5. And then lastly, we stop at 5 plus 1 is 6. And of course you see, hey, that's the same exact thing. So I've written two different looking formulas that of course can, or sigma expressions that can represent the same exact sum. Lastly, this one appears a bit esoteric, but will make a lot more sense in context in maybe 3 or 4 lessons. So as I goes from 1 to n, the first thing we're going to do is substitute in here, and we get f of x sub 1 delta x plus f of x sub 2 delta x plus, that thing will go on for quite a while, f of x sub n minus 1 delta x plus f of x sub n delta x. And just to give you an idea of what the heck this thing is, well, first of all, make sure you understand the notation. I went from 1 to 2 to 3 to 4 to... I just put this penultimate term in here, the second to last term. It's not absolutely necessary that you list it, but it is best practice so that everyone can see the pattern clearly. And then the last one is f of x sub n delta x. Think about what f of x sub 1 could be. Well, usually those translate for us into y values, right? So it's really a y value times some change in x. Just think of that as a little width. So if you think about this, actually what this thing is it's a height of a rectangle times a base of a rectangle. Or just think of it as height times base, right? Where the y value is going to be the height, and then that'll be the base. So effectively, what we're doing is we're taking a function and we're adding up a bunch of little rectangles, one next to the other. Right, f of x sub I delta x is that length. Not real important that you understand that right now. We'll get into very, very great detail on that sometime soon. There are a few things you need to understand, or a few formulas that basically, if you know, they make dealing with sigma a lot more simple and a lot less tedious. So I'm just going to get rid of the rest of this. Actually, I'll leave that one up. The first one is this one. And again, this is on the PDF. And basically what this is saying, if I'm going from 1 to n, I'm adding up some c value, that is to say, a constant. So let's just pretend for a second that this thing is 5. It would be 5 plus 5 plus 5 plus... And then the question is, how many times do we keep doing this? Well, n times. So really this is basically n terms of 5 plus 5 plus 5 plus 5 plus 5, which is, of course, by definition of multiplication, equal to 5n. So in general, as I goes from 1 to n of some constant, that sum is simply the constant times the n value. And again, right now it's sort of like, well, where's all this coming from? What I'm trying to do is just get you to a point where You're more comfortable with sigma so that when we deal with it in a calculus context, that there is at least a knowledge base that we're moving from. Okay, the next one is more interesting, and it involves a story. Ooh, how wonderful. So, two stories. So, as I goes from 1 to n of I. I've actually strategically left this one up here because this is basically a numerical example of this more abstractly written sigma expression. So that's an I, just so that you're clear on the video there. This one goes up to 6, and it adds up all the numbers up to 6. So quite a long time ago, over 100 years ago, there was a little boy. This is story number 1. A little boy named Gauss, and he was sitting in his. It's sort of a mythical story, so we shouldn't. I'm not declaring any factual history here. Gauss is in his class. He later becomes a very famous mathematician. Maybe you've heard of the Gaussian distribution or any number of things. So anyway, Gauss is sitting in his either kindergarten or first grade class. Let's just say it's first grade. And his teacher is totally fed up with all the classmates and Gauss himself. His first name, by the way, is Carl. So the teacher says to all the students, I want you to just sit down and I'm going to give you a lot of arithmetic to do. She's thinking this will take them a really long time and it'll keep them quiet, and if they don't do it, they'll all get bad grades or whatever. So she says, you all sit down and add up the numbers from 1 to 100. In other words, 1 plus 2 plus 3 plus 4 plus 5, all the way out. You can see we've done a very simple calculation, or a very small calculation of 1 through 6 is 21. But effectively the question she poses to her little student Gauss and all of his classmates is this. And Gauss thinks to himself, well, he starts to write it like this and realizes that, and I know I've written it a little bit strangely. I've included the first 3 and the last 3 terms and then a dot, dot, dot. But I've done that on purpose. Because Gauss is thinking, well, I shouldn't spoil the thinking with, the story. So the class then takes this problem and sits down. And within a matter of seconds, little Carl Friedrich Gauss raises his hand and says, I got it. And the teacher says, there's no way. And he says, it's 5,050. And she, of course, the perfect stereotypically angry first grade, first grade teacher says, I'm going to go sit down. She sits down at her desk, and 20 minutes later, she pops up and she says, he was right. And the question is, how did he do that so quickly? And the line of thinking goes as follows. There's a few ways of thinking about this, but I found this one to be the simplest. If we write the numbers from 1 through 100 here, and we pair them up, that pair that I just connected, 1 and 100 makes 101. 2 and 99 makes 101. 3 and 98 also makes 101. And now you're basically thinking, well, there's 50 pairs of 101. 5,050. I guess you could also, and now I guess to dissect this 50 a little bit more, first of all, 101 is just one more than 100, easy. The 50 comes from the fact that there were 100 original numbers, and then we're dividing that by 2 because each of them will pair off. So in general, the formula will be, we'll see if you can write it for yourself, but if you, now hopefully you've paused the video and done that, you'll get n times n plus 1 over 2. Remember, the n over 2 comes, that's 100 divided by 2 is 50, and then 101 is clearly n plus 1. So there you have it. That's a way to add up the first, if somebody says to you, add up all the numbers from 1 through 50, you could just simply say, oh, well, that's 25 times 51, and once you have that calculation done, you're finished. Okay, so I guaranteed you 2 stories, and the second story is me in a sophomore class in a computer programming class. in college. And I was a math major, so I was atypical in that class because most of the computer science people who were computer science majors, this was in a C++ programming class. Most of those students were freshmen because they were computer science majors, and I was just there because I figured, why not take a computer programming class because I was a math major. So I had already heard the Gauss story from a math professor, and the first programming task that my computer science teacher had us do was this exact question. He said, computers are so powerful, they'll allow you to add the numbers from 1 to 100 in a blink. And picture for yourself that this is in sort of stadium type seating. There's a few hundred people in the lecture, and the professor says, so let's do 1 plus 2 plus 3 plus 4 plus 5 all the way out to 100. And he was trying to make the point that, of course, this computer is ultra powerful and the human brain just doesn't measure up. So I'm in the upper deck here, and I raise my hand, and he says, yes, sir. And I say, it's 5,050. I scream this down from the top of the audience. And all these heads look back, and the professor says, you're right. How'd you get that? And I said, well, I did 1 plus 2 is 3. And then 3 plus 3 is 6. And then 6 plus 4 is 10. And then I just kept going, and I just got them all. And then by the end of you talking, I had 5,050. And these kids in my class, keep in mind they were all 1 year younger than me, so I was like really comfortable with the whole scene. And they looked at me like I was insane. So a couple weeks go by, and I'm walking through walking in the streets to class, and there are kids from that computer science class who would look at me like, that's the guy who had all the numbers up. And of course, right after the class, I went up to the professor, and I was like, yeah, I was just kidding around. Obviously, I knew it was n times n plus 1 over 2. So good times. So let's now use our information. I'm sorry, there are 2 more that would be useful for you. I equals 1 to n of I squared. That's n times n plus 1 times 2n plus 1 over 6. And then there's also I cubed. I'm not even going to write it out. There's another formula there. Not so easy an argument can be made, but a pretty easy argument can be made to develop either of those. And actually, you should be able to prove them by induction. So any of these can be proved just by a simple math induction argument. It might be simple to me, but maybe you have to go back and really think hard about how those proofs might work. And for you HL students, you will be, of course, potentially held responsible for proving such things. Okay, so I'm just going to apply this really quickly to this problem. I equals 1 to n of I plus 1 over n squared. So the first thing I see here is that this is not, that I is not dependent on, or this expression is, the n squared is not dependent on what I is. So what I'm going to do is factor the n squared out. And also a property of these sums is that you can split these 2 terms up. So this is the sum of the i's, this is the sum of the 1's. And of course we're still going from 1 to n. Now Gauss taught us that that is n times n plus 1 over 2. And we made a simple argument that that's adding up a bunch of constants, so that's really just 1n, or n. Now if you simplify all this stuff, you'll get yourself to some kind of reasonable answer, just some real quick work. Well, I'm not even going to bother. But you could simplify that, or you could leave it as it is. And for example, on the PDF I asked, use the properties and formulas to simplify the following and find the sum of the first 1,000 terms. I could plug n equals 1,000 into this expression and immediately know the sum of the first 1,000 terms of that series. So these things can be pretty useful and efficient. Thank you.